All right, hey everybody. In this video, we're going to go through the subatomic particles. That means the parts of the atom. And we're also going to learn how to draw models of atoms from the periodic table. So you may have learned about atoms previously, and here is a very basic model of an atom. We talk about an atom having a nucleus or a middle and electrons that sort of orbit around the outside edge. So real quickly, what is an atom? An atom is the smallest part of a chemical that exists, right? That means an atom of gold, for example, is the smallest form of gold before it doesn't become gold anymore, right? So it comes from the Greek language and the adjective atomos, meaning indivisible or unable to be divided anymore. Now, throughout time, we've had a different understanding of what an atom looks like if we were to be able to see it. Of course, we can't. So we use this idea of a model or some representation. It started out thinking that it was kind of just a solid, small piece, right? And then we maybe understood that it was kind of solid, but had separate particles in it that we could uh, that could be talked about, right? Sort of like a chocolate chip cookie has the cookie and the chocolate chips. Then Rutherford in the early 1900s said there's a middle part to it, right, and other things surrounding that. Niels Bohr later said middle part, things surrounding it, but they are not touching necessarily, right? So they kind of orbit around like the solar system, the planets orbit around the sun. And then Heisenberg and Einstein and Schrodinger, others more recently determined that it's more like a cotton ball. There's a lot of air space in between it all. But we can't really be sure exactly where the electrons are, so we can't really draw them separately. And you may have heard of these terms. These are going to be vocab that we should know about throughout this unit. So there are three subatomic particles: protons, neutrons, and electrons. All right. So protons and neutrons, you'll see here, are found in the nucleus. Okay. Protons, starting with P, have a positive charge. Neutrons, as the name implies, have a neutral charge or no charge to them. And then electrons, which are much, much, much smaller than both of these other pieces, have a negative charge. So notice on the bottom here, when we talk about the mass of atoms, and obviously we can't feel atoms individually, they are much too small. But the mass of an atom is made up of the weight of its proton and neutron. The electron is essentially zero, right? So we don't consider that to be a big part of its weight. Now, what is an atomic mass unit or an AMU? Well, one atomic mass unit is 10 times 10, 1.6 times 10 to the negative 24th grams, right? So you can see how many zeros as a decimal that is there. It'd be like one paper clip weighs about a gram. All right. So if you could cut a paper clip into 1 with 24 zeros pieces, one of those pieces would be about as much as an atom weighs. Okay. So as we go throughout these notes here, there are going to be things highlighted in red. Let's go ahead and write those down, get those into our notebook somehow so that we can remember them. Where are these subatomic particles? Well, if you remember the beginning, we talked about a nucleus being the center part. And that nucleus is made up of the protons and neutrons. Okay. And again, those are what make up the mass or weight of the atom. Okay. Electrons orbit around in what we call an electron cloud, super, super fast, almost the speed of light. And so we draw those around the outside. All right, now when we look at the periodic table, each element on the periodic table has a box that looks about like this. It's got some key information in it. The symbol, okay, chemical symbol, which is a letter or two. First letter is always capitalized. So if it's just a single letter, it's always a capital letter. If it has two letters, it is always a capital letter with always a small letter next to it. The element name shows up underneath. They are named from Latin and Greek root words, so they may not always match the chemical symbol letter to the name of it. Lead is a good example for lead. The chemical symbol is Pb. but the name is lead. There are others. Atomic number shows up in the corner, and that identifies how many protons exist in that atom. Okay, that number, if that number changes, the element changes. So fluorine will only ever have 9 protons. If it becomes 10, it's a new element. If it becomes 8, it's a new element. And then at the bottom, you're going to see the atomic mass. That's usually a decimal number. And we'll talk about that in just a little bit here. Essentially, the atomic mass is the weight of the protons plus the neutrons. Okay, feel free to pause or go back, but real quick review. 3 subatomic particles you need to know about: protons, neutrons, electrons. Okay, protons positive, neutrons neutral, and electrons negative. The atomic number equals the number of protons. Okay. And then remember that only the protons and neutrons count towards the mass. So for example here, we can round 15.999 to 16 in oxygen. Oxygen has 8 protons, so we take the mass, 16, minus the 8 protons, which tells us there are also 8 neutrons. Okay, I'll show another example of that because those two numbers are not always equal. What are always equal in uncharged atoms, atoms that do not have a plus or minus charge to them, they're neutral atoms, the two numbers that are always equal are protons and electrons. And that has to be the case because protons have a positive charge, electrons have a negative charge. They have to cancel each other out, okay? So here we have boron, number 5. Boron has 5 protons because it is atomic element number 5. In an uncharged boron atom, it will also have 5 electrons so that the charge cancels each other out. But if we look on the periodic table, the atomic mass of boron is about 11, right? Remember, boron always has to have 5 protons, okay? So 11 minus 5 is 6. And the two parts that make up the mass are the protons and the neutrons. So 11 minus 5 equals 6. It means there has to be 6 neutrons in boron. All right, another term you will hear as you read or research or as we talk about atoms and elements are isotopes. Isotopes mean atoms of the same element that have different numbers of neutrons. Remember, they have to have the same number of protons as labeled on the chart, periodic table. Uncharged atoms then have protons and electrons numbers equal, but they can have different numbers of neutrons. Okay, so you may have heard about carbon-14 dating is a way to tell how old something is, right? Carbon-14 is a isotope of carbon-12. All right. So again, that number tells us how many neutrons they are, and that number can vary. It can be different. Another quick review. All atoms of the same element have the same number of protons. Okay? Hydrogen only ever has 1 proton. Helium always has 2 protons. That's what tells us what atom it is and what gives it its property. In a neutral atom, the number of protons and electrons are the same, so those charges cancel each other out. Okay? So why do we use models, or why do we think about what is a good representation of an atom? Because they're infinitesimally small. So they're so small, we can't study them individually. We need models in order to understand how they behave, what they do. So remember I was talking about the cotton ball model, and there's a lot of air space in there, but we can never really know exactly where the electrons are. Think about it a little bit like this. The electrons are kind of like the blades on a fan, moving so quickly, and even though they're separate things, because they move around randomly so quickly, if we were to try and touch any area of a moving fan, we would touch something solid, right? Because it's moving so fast, okay? Even though we may stick our finger through into an airspace, the rapid movement acts a little bit like a solid. That's why that cotton ball idea is kind of a good representation of an atom. All right, so the electrons orbit around a solid center, the nucleus, okay? And what we're going to do as the wrap up to these notes here is learn how to draw what are called Bohr models. So Niels Bohr was a famous scientist who discovered a way to, or developed a way to draw out models of atoms. We're going to do that. And remember, anytime we draw a model of an atom, it's like we take a picture that's frozen in time, okay? Because atoms are constantly moving. And remember, when we draw these, we're not drawing them to scale, right? We're not measuring out how far the electrons are from the nucleus and such. So it's just a way for us to show and represent. Okay, so in the nucleus, we're going to use numbers and letters to represent the protons and neutrons. So if, for example, we were going to draw element number 10 here, right? We would know immediately 10 protons, okay? And we would have to do the math from the periodic table to know the number of neutrons. And then we're going to draw electrons around outer rings, and I'll show you those in just a moment. We're going to draw them nice and big, though, so we can count the number of electrons and see them. Okay, those electron orbitals are also called levels or energy levels. Sometimes they're called energy shells, and that'll come up more as we talk about bonding of atoms. But what's important to know is that energy levels, energy shells of electrons around an atom have more energy the farther out you go from the nucleus. So level 1, closest to the center, the smallest ring in the middle, has a low amount of energy. And that low amount of energy also means it can only hold 2 electrons in that ring. All right. As we go to levels 2, 3, and 4, each of those rings can hold 8 electrons until they're what we call full. And then we need to go to another level. So as we draw these, we'll be able to see that. So first off, we're going to write the elements symbol. Then we're going to do some calculations to figure out protons and neutrons. All right. Then we're going to draw some electron orbital rings, levels, and make dots on there that are nice and big and visible for the electrons. Okay, and then we draw each shell or ring around until each one is full and we have the number of electrons that we need to match the number of protons. So using fluorine, let's try this as an example. You can write this in your notes. Okay, fluorine is atomic element number 19. Is number 9. The mass number of fluorine is 19. Okay, so if we try to figure out how many neutrons there are, we take the mass number, 19, minus the number of protons we know it has, because that matches its atomic number, 9. That leaves us with 10 neutrons. So in the center of our Bohr model that we're going to draw for fluorine, we're going to write 9p plus, 9 protons, and 10 n0, 10 neutrons. We also know, because this is going to be an uncharged atom, that there will be a matching number of electrons to the number of protons, right? Plus and minus need to cancel. So we know we're going to end up with 9 electrons, okay? And we have to follow our rule of these energy levels, all right? So in energy level 1, we wrote in the middle our 9p plus, 10 n0, okay? First energy level ring around that, a circle, we're going to fill with 2 electrons. And you can draw them on each side like this. Sometimes people draw them right next to each other on the ring. The important part to know is that that ring can only have 2 dots on it, 2 electrons on it. And then we need to draw the next level, energy level 2, around that, okay, which can hold up to 8. So we could have, if we filled both levels, a total of 10, but we only need 9. Fluorine is 9. So we're going to fill it with 2, 4, 6, 7 in this level. It's not a full level, number 2. Plus those original 2 gives us the 9 total that we need. All right, you try this on your own for aluminum, same process. What's the atomic number of aluminum? What's the atomic mass? Do a little bit of math, write your letters in the middle, and then follow the rings rule to fill it up to match the number of protons. So pause the video here while you draw that. And here's your answer to double check it against. And that's all we got.